on a periodic function. Okay, so what is a function? Well, the easiest way for us to explain to you is to show you an example. As you can see, as time progresses, the distance travelled increases. This shows that there's a relationship between the distance travelled and the time that's passed, and therefore distance is a function of time. That is essentially what a function does. It shows the relationship between two or more variables.
Right, now we can also think of functions as machines, like the one up there, which take something as their input, apply some kind of process to it, and give us an output. So in this case, our input is the time that Thomas has been travelling for, and our output is the distance that he's travelled. Now, if we go back and look at our graph, which should be up there, we can see that the distance in metres is always double the amount of time in seconds. So at 1 second, it's travelled 2 metres, at 2 seconds, it's travelled 4 metres, and it goes on like this. And from that, we can say that our process is a doubling. Now, let's say I don't know what my point in time is. It's completely random. So I'm going to call it x. As Hannah said earlier, distance is a function of time, which in this case is x. So I can write that like this. Now, what our bottom machine here is showing is that our function of x is always double x. But if I wanted to show that every time, drawing that out is going to get a bit repetitive and annoying. So I can write it out in another way, like this. And this is what we call function notation. It's just a far easier way of displaying functions. So, since I've shown my function of x is 2x, when x is 1, I get 2. When x is 2, I get 4. You know where this is going.
So now I'm going to tell you about the periodicity of a sinusoidal wave or a function. You probably ask yourself, what is a sinusoidal function? Well, a sinusoidal function is any function that uses the function of sine. So using Dennis's notation, you can say f of x equals sine of x. The function of sine is a periodic function. A periodic function is any function that repeats itself, so the definition of a period is how long it takes to repeat. Periodicity is the measure of how big or how small the period is. You can also change the period by manipulating the x, so sine of 2x halves the period, is doing twice as many cycles in the same time. Also, sine of half x doubles the period, is taking twice as long to do the sine wave.
So, as Jake's mentioned, we can change functions in a few basic ways. We can stretch them vertically, we can stretch them horizontally, and we can also kind of pick them up and shift them where we want. But that can only really take us so far when we're trying to build a good periodic model. And to get any further, we need to start talking about how we can add functions together. So, I'll demonstrate this with the sine curve, which you're not familiar with. We can do this visually by drawing two functions on the same set of axes. So if you imagine the blue function is behind the red function, then I know I know that at the peak of the wave, they both have a value of 1, and 1 plus 1 is 2, which is why we end up with a function which is twice as big. And this can also happen in reverse. So we see here that the red function is the upside down version of the blue function. So I know that at the peak of the blue function, it has a value of 1, but at the trough of the red function, it has a value of -1. 1 plus -1 is 0, which is why we end up with a straight line. And this is actually really useful, for instance, if you're building a cinema. You don't want to be sat somewhere where you're going to get deafened. You want to build the speakers so that they don't cancel out, because you want to hear the movie, but you don't also want to kind of get a massive earful. And it's also useful if you're building a theatre, a lecture theatre, because you want to be able to hear me, and I want to be able to hear you if you're talking, and I don't want you to. We can use this to model a variety of phenomena, such as signal, and using inverse applications such as signal processing, acoustic engineering, computing, and quantum mechanics.
So it turns out that we can actually express every single periodic function in existence as lots of sine functions and cosine functions combined together. This is called a Fourier series, and it's very useful as we can take a fairly complex problem and break it apart into lots of simple terms that we know how to deal with. So take the example of this function. We call it a square wave. in its normal form, then certain things are quite difficult to do. But we can actually express it using the Fourier series as an infinite sum. And, well, an infinite sum might appear quite complex. In certain circumstances, it is a lot easier. And so, yeah, we can manipulate this function in ways that we couldn't before. And, yeah, you can approximate every single wave in existence in this way.
The Fourier series can be used in many ways, from checking the roundness of biscuits on a production line to predicting time. But one of the most important uses of it is its ability to make lossy data compression possible. Lossy compression is a way of reducing a file by permanently eliminating certain information. For example, using the Fourier series, we can convert an audio signal into a sum of lots of different waves, and then back again. But in the process, we can delete the parts that won't be noticed. Here we have an audio signal made up of lots of different waves, but as we delete some of the components of the waves, not a lot of difference is made to the sum of the waves. As you can probably tell, this will drastically reduce data, as we only have a small portion of the file that needs to be stored without reducing perceived quality. One of the top 10 apps in the world is Shazam, which, for those of you who are not familiar with this app, is an app that allows you to identify any TV show or song that's playing and allows you to search for it or purchase it. This actually identifies music by comparing the Fourier decomposition of recorded sound to a data resource of Fourier decomposition of known songs.
Now, we've all heard of musical chords, and the musicians in the audience will be able to tell you that the chord of A is made up of the three notes A, C sharp, and E. Now, when you hear a chord, you're only really hearing a conglomeration of its constituent notes, and it's in this way that music follows the Fourier series. The notes A, C sharp, and E all have their own individual sound wave, and when played together, they complement each other to create one large wave. Hence, a chord is born. In a similar fashion, we can model the tides as a mixture of all the tiny factors affecting the waves. We use different mathematical models to predict certain factors of oceanic motion, such as the wave height, the water velocity, and even when the high and low tides are. However, since there are so many factors that go into changing the ocean's movement by even a tiny amount, it becomes immensely difficult to fully accurately predict the aquatic propagation, which is just the way that the sea moves. Such factors include the density of the water, the wind, water levels rising because of a changing climate, or even the shape of the seabed. All of these change the way that we predict tides, so it's clear to see why there isn't just a general timetable which can tell you years in advance what the tides will be like. All in all, the Fourier series is useful for predicting tides, telling us more about music, or in recent discovery, it's even shown to help cure cancer. So, I guess you could say that the Fourier series is pretty darn ace.